the Millikan oil drop experiment. As you go through physics and you get into kind of studying electric fields, voltages, you will probably run into this oil drop experiment, and it's worth understanding the reason why we had to do this experiment, or at least why Millikan was trying to do the experiment. And the reason was mainly to try to see and formulate the experimental results that charges are actually quantized. Now, we know that right now, and you have probably studied this kind of on the introductory side to charge, and I can put up a link up above there, so you probably would have seen that already. However, you wouldn't have at the time enough of the kind of background to be able to take on and try to understand an experiment like this. Now, what do we mean by quantized? Well, quantized is kind of a discrete format. So if you take a look and you try, let's say on a continuous axis, you try to draw out. Now I'm going to take this and let's assume that these are charges. So if you wanted to measure the amount of charge, well, what we have noticed is that charge, so there could be, zero charge altogether, and I'm going to be referring to just the magnitude of the charge. Notice that right here, we have the charge on an electron, which is either a positive, which means the lack of an electron, so that would be on a proton, okay, and then negative, it just means actually on the electron. And we have this particular charge. And again, I believe that you have seen this in the past. Now, the quantization process means that, well, anytime you want to be able to measure how much charge it has, it turns out that this actually is in discrete form. So there could be, one electron, okay, lack or excess of electrons. Again, I'm just referring to the magnitude. 2 electrons, okay, 3 electrons, 4 electrons, and so on. And it turns out that there is actually no charges that fall in between. We can't find charges on particles that are charged either positive or negative, so lack or excess of electrons, that are falling in between. So we don't see that at all in nature. And it turns out that this is a fundamental constant of nature, which this particular number now we've gotten way, way better than Millikan has, because he was doing that kind of in the early 1900s. And now our actual experimentation, our measuring tools have gotten better. So, we've been able to approximate this charge. And it turns out that every charge that you have is some multiple. So this is just n. So how many of these particular lack or excess of electrons you have. So it might be 1, okay, which would be the smallest amount. You can't get any smaller. So sure, maybe you have heard of things like quarks, okay, which protons and neutrons, okay, they do kind of are made up of some of those. However, in terms of charges, we really have the smallest unit as the charge on a single electron. And then the lack of an electron would be, okay, on the positive side of the actual charge. So how did Millikan come up with an experiment to try to prove this, to try to show that indeed you have these quantized formats, and then there's really no actual charges that you can find that fall somewhere in between? Now, of course, you might say, well, because he was doing it so early, then, his experimentations probably did show him that he might have something in between, but that would be due to just simply calculation errors in terms of trying to figure out, very small masses and so on. So let's jump into this Millikan oil drop to try to show this quantization of charge. So how did Millikan go about this? And so he decided to do something like this. He took almost like a spray bottle that you would have, and that spray bottle was filled with oil, and then he would mist it, kind of like a perfume, okay, that you would have, and then he would mist it up. And then what he would try to do is the following. So he would have 2 plates. So you can imagine, here's one plate, here's the other plate on the opposite side. And now, because you have come to the point where you're familiar with potential differences, meaning voltages, so he tried to do this. So he basically said, all right, well, let's hook this thing up. So we're going to hook this thing up. okay? So these two particular plates that we have, and we're going to hook it up, okay, to some kind of a battery. And this battery is going to have a varying, now this symbol that I drew there, that means it has a varying voltage. So we're going to have a varying voltage, okay, across. I'm not going to, you can drop the delta there, you can just write voltage. And then what he would do is he would set a positive and a negative amount. And then as he would spray the little oil particles, okay, these droplets of oil, what he wanted to accomplish is this. He wanted to accomplish to have one of those oil drops, okay, that just hangs in there, that just gets suspended, right? So as he turns on this voltage, so it creates an actual electric field. So this particular electric field that you would have, so it points from positive to negative. So we have this electric field that is pointing in this direction. He is setting the actual voltages so that he can measure them. And then he has this item which is suspended. Now, why in the world would it be suspended, and why did he want to do that? Like, why did he want to suspend this thing? Well, the idea behind the suspension, he was thinking that, oh, well, if I have this, and I'm going to take this out of here so that I can draw a free body diagram on it. So if I have this, I know that there is, okay, kind of an electric force that is pointing this. So this would have been the force coming from the electric field. And we're assuming that these are going to be kind of on the positive side because they are suspended, okay, so within here. So this is pushing it upwards. So it would try to, if it's a charge, you know, so it would be a positive charge, because if it was a negative charge, it would have just shot out, okay, in terms of trying to see it, it would just fall right back down, okay, to the positive. Now, why, okay, would this be suspended, and how do we know that this is positive? Well, because there is a force which must be upwards, okay, that you have on this if it was positive, and then it would be balanced off by the force of gravity, which would be pointing in the opposite direction. So that's why I say that it has to be positive in this case. So we know that this charge that we have no idea what that charge might be. At least Millikan didn't know. He wanted to find what this charge was, but he knew that there was a balance, right? And force of gravity would always be downwards. So if it was a negative charge, then the actual force from the electric field would have been downwards as well, and then oil drop would not be suspended. So that's the first step. First step is, all right, so it's some positive charge. Now, we know that all of these particular charges, okay, that we have in here, we can kind of take a step back in here and say that, well, what do we know about charges and voltages and electric fields? You know, how are all of these things kind of related together? Well, first off, we know that the voltage is nothing else but the electric, okay, so this is the potential kind of a difference on the energy side from the electric amount. So the electric potential is nothing else, and this is divided by Q. So this is by the definition of what voltage actually is. Okay, so that's great. So we know this. Well, what else do we know? We know that the electric field, and this is coming from exactly this and manipulating that, and I can put up a link up above there to that. We also know that this is nothing else but simply just the actual voltage potential difference that we have divided by the kind of displacement that we have, or the separation between the plates. So you would have a certain separation within here between this plate and that plate, which we could possibly measure. Okay, well, so if we know this, okay, and we know this, because we're setting, or at least Millikan did, he's setting this voltage across. So that means he knows what the electric potential is. Okay, so that's great. Now, why would he want to know that? Because the force coming from the electric field on the charge, please recall, and remember that this is nothing else but the charge multiplied by the electric field. And again, this is due to the fact that you were studying these particular forces. So we have this. Now, we want to be able to find out what this Q is, right? What the charge is. And now on the opposite side, the force of gravity is nothing else but mass times gravity in this way. All right, so I have these. Now, this charge is suspended, so it is in equilibrium, which means that these two which is the force coming from the electric field and the force coming from the gravity, must be equal to each other. Well, if they're equal to each other, then that means that QE, so the force coming from the electric field, is equal to the force of gravity. This is by the equilibrium, and we have this very simple equation. And this is what Millikan was looking at, and he concluded, and he said, oh, okay, well, if I wanted to know what this is, then all I would have is simply that my charge, if I wanted to find this out, is mass times gravity divided by the electric field. But hold on a second. I know what the electric field here is. And that electric field is equal to the voltage, okay, the potential difference, divided by the separation. And I know those two things. So if I substitute that in, then what I will get is that I'm going to get delta V over here and then delta D over here. You can convince yourself by doing the substitution. And now I have gravity, okay? I can measure the distance, the displacement. I am setting the voltage. So really the only thing that Millikan was missing was this mass, right? What is the mass of this particle? And that wouldn't have been very easy to calculate. But because you knew a little bit of physics, and so do you, you will recall that the overall thing, what we can do, is to find out what this mass is, and therefore we would know what the charge was. If we now have this suspended, but we turn off the voltage, so if we turn this off, then we get rid of the electric field, and therefore we get rid of this. So if we no longer have this, then what's going to happen to this particle? Well, gravity is going to pull it down. And that's what Millikan was doing, and he would see this particle fall down, and he would be measuring the actual speed, okay, as it would be hitting the bottom plate. Now, why would he want to know that speed? Well, because he would know the initial speed, which was 0, right, from the time of suspension. He would know the final speed, so this he would find out and measure it out. And therefore, if he knew that, and then how long it took, he could find out the acceleration. And don't forget that the net force, right, as this is accelerating, is just mass times the acceleration. So now, this net force, when there's no more electric field, this would only be consisting of the force of gravity. And then, he can also measure, and you would consider also the force of friction coming from the air. So you would have these two things, okay, kind of in a balance, force of gravity down, force of friction in the opposite direction. So he could find these things out. And then the acceleration was nothing else but simply your final speed minus your initial speed, which was 0, divided by the time that it took. So he would have this, and then he would be able to obtain the mass. And that mass would go right here. So I hope that this doesn't go way beyond you, right? So he's just using all of these things that you have learned from dynamics and then from the introductory side on charges and then the electric fields and potentials to run this experiment. Now, you might say, well, how does this now show us? So he can calculate this Q, okay, if he had all of this data and information. If he has the mass, well, we know what the gravitational force is. If he has the displacement between the plates, and he has the voltage potential as well, which he was setting. So he has all these things. But he can't guarantee that he's going to be finding out this elementary fundamental charge. So what he ended up doing was he kept running this experiment over and over and over. So he would be doing this hundreds and hundreds and hundreds and probably thousands of times. And then what he would be doing is he would just be placing, and he would be finding out that as he does these measurements, then what constantly would be happening, that his actual charges, so as he would be computing for different particles that were suspended, right, he may not guarantee that they were the fundamental one, meaning just single electron, right? But he would find, oh, there was, some experiments that he would run, and then they would fall very near, maybe 4 times the actual charge on an electron. Now, he wouldn't know that yet. But then, so they would cluster around. So they would cluster around these particular points, right, as he would be doing these computations. And then he concluded, so through experimentations, and he said, oh, my experimentation by error when I do some of these measurements and calculations, maybe they're not falling exactly at 2E or 3E or 10E or, whatever it might be, but I'm noticing that they're constantly falling in between these clusters, and none of them are falling in between here, right? Or as they were going in, so they would be just clustered around. And that's exactly what the Millikan oil drop experiment was all about. So then he can say, all right, so there is a difference in between this and this, this and this, and what is that smallest difference as I now start to calculate? And he found that it was approximately, 1.6. Now again, I don't know, okay, what his value actually was. Maybe you can look it up. But, nowadays we've been able to do these experimentations with way, way more accuracy and many more significant figures. This is to 4 significant figures, which is more than enough for you as a student studying fundamental physics, okay, within here. But you can look up how many sig figs that we currently were able to measure this to. So I hope that this kind of makes sense to you in terms of the experiment that he has done it. And it was a pretty clever one that he would have, because the suspension and that allowed him, and then, doing all of the calculations to find the charges is pretty unique. All right. So now let's take a look and try to apply it so that you can see this thing in action. So here's a very simple kind of process with the experiment, which would maybe be one of the experiments that he would have done. And let's see, based on what we know now, okay, what calculations you could be asked for as a student, and so that you can understand this. So we have an experiment, okay, so it's kind of like a Millikan experiment. And we have a tiny particle, and we know what its mass is. So we have a particular mass, okay, so that mass has been set, measured in maybe some particular way, and now it's being suspended between 2 plates having a potential difference of 450. So just like we have in here, so we have this suspension in between. I'm going to just copy and duplicate it. Let's bring it back down. Maybe I'll clean it up a little bit. So what we have is the following. So we know this. So we know that we have this, okay, it's being suspended. So we know the difference which is given to us, okay, within this question. So as we keep reading, the separation is 4.9 centimeters, right? We have the potential difference. So let's put that in here. Okay, so there is some difference, okay, within here. It's 450 volts. Okay, so from that 450 volts, we can obtain, because we know the 4.9 centimeter separation, so we know the electric field. So the electric field would be the potential difference divided by the actual displacement. Now, let's not forget, I'm going to turn this back into meters so that we have metric standard units. So it's volts per meter that we have, or again, remember that it could be newtons per coulomb. That's the same thing. So we have the electric field. All right. Now, if this is being suspended, okay, so as you're going through, we want to find the charge on this particle. Okay, so if we wanted to find the charge, again, don't forget, so this would be that the force of gravity, okay, must be equivalent to the, so within here, so as you're going through, this would have been your force coming from the electric field. Now, it doesn't mention, right, so in terms of suspensions, if there's positives or negatives, or which one is, so we will make an assumption. If they give you more information, you can certainly take a look at that. Okay, so I'm going to assume that this is kind of on the positive side, this is on the negative side because it's suspended. If it's a negative charge, then that means they have to kind of be flipped over. So positive would have been above and negative would have been at the bottom. Okay, so within here, so 2 things can happen. And now these 2 must be equal. All right, so these 2 are equal to each other. And now from here, so again, if they're equal, that means my force coming from the electric field is equal to the actual mass times the gravity. So within here, so that means my charge is going to be mass times gravity divided by the electric field, or you can certainly use your actual equation, okay, within here. So that's this one. So that's all up to you. So Q is equal to times G times delta D divided by your actual change in voltage potential. Now I have calculated this, so it's fine. So you can use either this or this, depending on what you have. So I have put this in here. Now we know the mass and we know gravity. We'll assume gravity is 9.8 meters per second squared. So let me substitute the numbers. So the mass, the gravity, the electric field, and let's compute it so we'll know exactly what that charge is. All right, so I'll be right back. So here it is. So you see it on the calculator. You can round. So if you want to round to two significant figures, because I think that's the lowest amount, so you can certainly do that, which would have been around 1.3 times 10 to the negative 18 coulombs. All right, so that's the charge. Now again, I'm assuming it's positive. So if it's negative, that means the potential difference would have been changed over. Now for the excess, so this is for part B. So find the excess or lack of electrons on this particle. So for this, so if anyone ever asks you about that, then don't forget that any charge is always the number, okay, of electrons that are in excess or that are lacking or a deficit. So in this case, if it's positive, so that would be lacking these amount of electrons. And then, you know, although we typically think of E just as an electron, but E is kind of your fundamental, you know, physical quantity that we have. So it's a constant of nature based on, you know, one lack or excess of an electron. And that is assuming, you know, I assume that it's 1.602 times 10 to the negative 19. So if you know the charge, which we have on the calculator, you can certainly then just solve for n. This we'll be dividing by, I'll put this in the bracket, 1.602 times 10 to the exponent of negative 19. So equals, and there you have it. So it's 7.99. And now we know that, you know, it can't be 7.99. So it would have been rounded, and this is just because of, you know, significant figures and measurements. So this, you know, would have been 8. So if it's a positive charge, that would have been an 8, you know, deficit. So that would have been your deficit or excess if it was negatively charged. So that will depend. So we have found the magnitude overall. And that is it, right? So now hopefully you know what the Millikan experiment was about. You know, it was about suspending the actual particles, and that was due to having, you know, an electric field which was causing a force, and then the gravity was causing the opposite one. And then Millikan was trying to balance these things off and then find out all of the charges, and then notice that they were falling basically in a quantized form, right? So there you have it. Okay, so happy studying, and this probably brings you to the end of fundamental physics for now. Okay, bye everybody.